In this video, I want to have a look at acceleration as a function of x. So in some cases, rather than the acceleration being written as a function of time, it's written as a function of displacement. So there's a lot of different ways that we can express the acceleration. So the one we're probably most used to when we introduce it is acceleration is the second derivative of displacement with respect to time. We can also say that it is the velocity differentiated with respect to time. But then there's these two newer looking ones, and we're going to go through and prove all of those. So we're going to start off with one that we're most familiar with. So we're going to have acceleration is the second derivative of displacement with respect to time. Now we know that that's the same thing as if we differentiated x with respect to t, and then we took that and we differentiated it with respect to t a second time. So we also know that that is the same thing, if we had that d dt, that our dx dt is the same as the velocity, so this whole thing could be written as dv dt. So we started with this one and we've got to this one now. But at the moment this is still in terms of time, and we want to look at it in terms of displacement instead. So using the chain rule, we could write it as dv dx is equal to, dv dx times dx dt. So that's splitting that off, and then that we know that our dx dt is v. So that's the same thing as writing dv dx times v. So that's this one here. Now we've got one more to get to. So if we now go from here, take it back up the top a little bit, from there we can write dv dx. We could also have a look at this v and alter this v a little bit. If we integrated that v, we would have a half v squared. So v itself is the same as differentiating this with respect to v, differentiating that whole thing. If we do that, that dv and dv down the bottom cancel out, and we just end up with the derivative with respect to x of a half v squared. So if we differentiate this with respect to x, that is equal to the acceleration. So that's our last one here. So in a lot of these problems, this last one is the one that you'll use to help you solve the problem, but sometimes we will need it in those other forms as well. Let's have a look at an example. So our first example tells us the acceleration of a particle is given by 6x squared minus 4x minus 3. The exact value, we're asked to find the exact value of the velocity when the particle is 2 centimeters from the origin. But we're also told initially the particle is at the origin with velocity 3. So that means at t equals 0, displacement was 0 because it was at the origin, and the velocity was 3. So those are going to come in handy in a little while. But at the moment we have that a is equal to 6x squared minus 4x minus 3. So if we rewrite that, we'd have d dx of a half v squared is equal to 6x squared minus 4x minus 3. So if we want to find a half v squared, we're going to have to integrate 6x squared minus 4x minus 3 with respect to x. So we'd have a half v squared is equal to, that would become an x cubed, which would change that to a 2, minus x squared, which would change that to a 2 as well, minus 3x plus c. Now we want to figure out what that c is. So that's where we can use these pieces of information up here. So we know that when v is 3, x is 0. So we could write in a half times 3 squared is equal to. Now because x is 0, those first 3 terms are all going to go to 0, so that's just going to give us c. So that means c is equal to 9 over 2. So that gives us a half v squared is equal to 2x cubed minus 2x squared minus 3x plus 9 over 2. Now we want to rearrange this just to make v the subject on its own. So I'm going to start back up here, and the first thing I'm going to do is go through and times everything by 2 to get rid of those fractions. So I'm going to have v squared is equal to 4x cubed minus 4x squared minus 6x plus 9, and then I'd have to take the square root. Now, when we take the square root, normally we take the plus or minus square root, but we have to decide which one of those we're going to use, because for a particular displacement, we can't have it being positive and negative velocity. That doesn't make sense. So we need to use this as well. We know that when x is 0, velocity is a positive 3. So that means we're just going to look at the positive square root in this case. All right, so we've got velocity in terms of displacement. but we're asked to find the exact velocity when the particle is 2 centimeters from the origin. So at x is equal to 2, the velocity would be equal to the square root of 4 times 2 squared minus, that should be a cube there, sorry, 2 cubed minus 4 times 2 squared minus 6 times 2 plus 9, which would end up giving us the square root of 13 centimeters per second. Our second example tells us that a particle starts at rest at the origin and moves to the left so that its acceleration is given by 8x plus 1 meters per second. That should be seconds squared there if we were talking about acceleration. Find its velocity when the particle is 5 meters to the left of the origin. So let's translate all of that first. This first bit, the particle starts at rest at the origin. So that means at t equals 0, v equals 0 because it's at rest and it's at the origin, so x equals 0. Then it tells us that it moves to the left. So that means that as time increases, velocity is going to be negative because it's moving to the left. We're also asked to find the velocity when the particle is 5 meters to the left. So we're trying to find the velocity when the displacement is minus 5. Alright, so let's start off. We know that a half v squared, that's our acceleration, is going to be equal to the integral of 8x plus 1 dx. So that means that's going to be equal to 4x squared plus x plus c. Now we can use these pieces of information to figure out what c is. So if we've got a half v squared there, v is 0, which would just give us 0 there. These first two terms are going to be 0 as well because the displacement is 0, which just leaves us with c is equal to 0. So that means that a half v squared is just equal to 4x squared plus x. Now we want to rearrange that to make v the subject on its own. So v squared would be equal to 8x squared plus 2x. And then we want to take the square root. So we'd have our 8x squared plus 2x. But again, we need to decide whether we want the positive or negative square root. So that's where this second part of that sentence comes in. It says it moves to the left. So if we want it moving to the left, our velocity has to be negative. So we have to have that negative sign in there. All right, so we've got the velocity in terms of the displacement. We want to find it when x is equal to minus 5. So we're going to substitute that in. So we'd have minus the square root of 8 times minus 5 squared plus 2 times minus 5, which will give us a velocity. It asks us to 2 decimal places. It'll give us a velocity of minus 13.78 centimeters per second. Actually, I think it should be meters after all, shouldn't it? If that's meters per second squared there. So that should just be meters there. So that's having a look at acceleration as a function of x.